I will take you on a little history tour of Sensei technologies to assess roadway and bridge deck conditions, and to set a contrast to what the Voters project is trying to do. Voters is a project that is funded by the NIST through the TIP program, which is a high-risk, high-benefit project. So we're not just aiming to incrementally improve the technologies that are currently used out in the field, so I will mention. We're trying to really get a big step forward. I also have to acknowledge Ken Mazer, the Realist. He actually helped me out with a couple of slides, and we discussed this in preparation of this presentation, so he's well aware of what I will be talking about. I also like to thank many Voters, team members, and collaborators. We have 4 joint ventures as part of the Voters project: Northeastern, the University of Vermont, UMass Lowell, and Trillion. Hopefully pretty soon we're going to have a 5th one with Earth Science Systems. Then we have the Northeastern collaborators of Census and IGERT, the Mass Highway and FS&T, and I'm sure there are some, I apologize already, that I forgot. After a short introduction of the problem that we're trying to address, I will talk about examples of commercial roadway and bridge deck sensing technologies, starting from a low-tech to a little more high-tech. I will discuss then the Voters concept and what Voters is trying to change and improve on those sensing technologies. In 2005, the ASCE report card gave the U.S. infrastructure a D. I suppose most of you interested in civil infrastructure will probably know about this. They claim that over 1.6 trillion is needed to improve the existing infrastructure to good conditions. I think we have a lot of evidence in the news of what things are happening, or we just need to look at our roads to see rutting, cracks, and all kinds of defects. For future monitoring or to put new infrastructure in place, it will cost even more. Congestion due to road repairs costs an estimated $78 billion annually in lost productivity and wasted fuel, which is an unbelievable number when we found this. The source is the 2007 University Transportation Center for Mobility Statistics. So it's quite obvious, I think, to everybody that there's a critical need for the right repairs in the right place at the right time. Okay, so how our roadway and bridge deck maintenance decisions are made right now? The answer is they're done by collecting condition data, and they're currently collected in accordance with the ASTM standards and then used by highway agencies or local municipalities to make public works decisions. If I talk conditions assessment, what are we looking at? And these are just examples. This is not supposed to be a complete list. On the pavement side, we're looking at rut depth, cracking, skid resistance, deflection, modulus, and thickness. On the bridge deck side, we may look at delamination, corrosion activity, chloride content, underside condition, cracking, patching. Most of this information that is measured in different ways will find its way in some kind of indices. One very commonly used one is the Pavement Condition Index, or PCI, which happens also to be an ASTM standard. I believe companies feed all this information in pavement and bridge deck management systems that help them to make the decisions. All right, I have a couple of slides now where we're going through technologies that are all currently used out in the market. And what's to point out here, we're going from low-tech to high-tech. We're going from low equipment cost to high equipment cost. The personnel cost is pretty much even throughout those changes in the technology. The first one, visual inspection. The ASTM standard to create the PCI says that you go out, you create a map of a certain area, you map out if you have alligator cracking, if you have cracks, which you can't really see, this is a little glare on it, if you have some shoving here. You cut out a certain area, you map it, you figure out what the percentage of the defects are, and then you just extrapolate that for the whole road, and that's your index. So obviously there's room for improvement to cover a larger area and take that extrapolation out of it. There are a lot of indirect measurements, and these are just a couple of examples as well. These are measurements that look underneath the surface. This, for example, is an impact ecosystem, an acoustic method that looks at voids and defects, the same with the portable seismic property analyzer. This is a ground-penetrating radar single-channel system that is just pushed along to collect as many profiles as possible. There's also something called chain drag, which creates an acoustic signal that can be detected to isolate voids or defects. One can also connect a half-cell meter to detect the rebar location, or can make efforts to detect the corrosion. All of those measurements are localized, stationary, or profile-based methods that require road closures. Now, to avoid road closures, people were trying to put all kind of measurements onto their vans. These are now vehicle-based digital surface condition surveys. So these vehicles only look at the surface, not at the subsurface. These two examples here that they use GPS, video profilometers, LiDAR, infrared. There's a host of systems that companies use in different combinations. With the collection of large visual data sets, video data sets at traffic speed, there is software emerging that automatically tries to analyze the road defects. This is an example from a software that is called Wisecracks. These systems help, but I think there's still a need for a human to check the results. Now this is again the subsurface level, vehicle-based, profile-based digital subsurface condition surveys. Again, they are divided up in acoustic methods, fall and weight deflectometer, or rolling wheel deflectometer versus ground-penetrating radar, two air-launched systems here. They're mounted onto trucks, on trailers, and they're driven in traffic. This one even has both systems on the same vehicle. Okay, I'll make one point here. This, if you have two of those radar channels here, you have two profiles along the width of the road that you observe data. Now, there are other companies who take this to another extreme. They take a whole radar array. So down here, there's 30 channels along the width of the car, which then gives you a full coverage of where the vehicle drives. Another improvement. There's also software emerging in different variations that merges the video maps that you could download with actual data, and this is like radar data. I'm not sure what the other data that are displayed are here, but you can have your own, connect your own sensors and display them in one synchronized way. So what are shortcomings of these systems? The area of investigation is still a very small percentage of the actual roadways and bridge decks. Monitoring of any deterioration is limited to a fraction of that small percentage. And surface sensing is much more common in subsurface sensing. However, a lot of the defects start developing in the subsurface, which makes it desirable to detect them before the damage is getting too large. Stationary point and slow-moving measurements are costly, in particular through traffic delays. And reflected in the ASTM standards, they're kind of lacking behind the technology, because the technology has now already the automated, for example, vision analysis of videos for cracking, and there could be a standard that could describe how you do that from video data, but it's really just described how you do that from manually, making a sketch and coming up with a percentage. This is kind of what is done today to analyze bridge and road beds. But now, 2 years ago, we wrote a proposal to NIST to kind of have a little shift in the paradigm here of how we go about doing this. VOTR stands for Versatile Onboard Traffic Embedded Roaming Sensors, and a good guess is while we wrote this proposal, it was election time. The VOTR's concept goes as follows. We use vehicles of opportunities. These are cars that drive around the city anyway. You could think of mail trucks, delivery trucks, buses, private volunteers, police cars, city vehicles. They're going about their usual business. They have a voter system or parts of it mounted to it. The driver does not have to do anything to them. The driver can maybe turn it on and off, but it does not affect what the driver does. It has a wireless connection to a control center, so how the operator of the system can maintain it. So these vehicles of opportunity, they collect sensor data containing surface and subsurface roadway and bridge deck condition at traffic speed. So the specification actually for the Voters project is to create sensing systems that can go up to highway speed, 60 miles an hour.